Good morning and welcome to the 25th episode of Home of the World's Worst Weather Live. My name is Ian Bailey. I am a meteorologist and education specialist, and I'm part of a crew of 6 observers that live and work from the top of Mount Washington, taking hourly weather observations, putting out forecast products, and conducting research from the top of New England. Before we dive into everything today, I just want to give a quick shout out for Memorial Day. Happy Memorial Day, and thank you to all of the men and women who are serving in our armed forces, and a huge thank you to the sacrifice of those who have fallen defending our country and her interests. So today is Monday, and it's one of our deep dive discussions, and today is tornadoes. So we have a lot to talk about. We're going to go ahead and dive into it in just a moment, but real quick, I want to show you what's happening up here on the summit. Currently, as you can see, it is a very calm day outside, just like it was on Thursday. We've had a very mild shift, and so our wind speeds are very calm, down in the 8-mile-per-hour range, substantially lower than what we're used to. Temperatures are quite warm, so we're slowly climbing towards the mid-50s at this point. It's pretty warm. It's the warmest, at least, it's been so far this year. Again, it just contributes to the really calm and pleasant conditions we're experiencing outside. We can see pretty far away from the summit. We can see 70 miles. There is quite a bit of haze as the ozone levels of the summit are at a moderate stage today, so we can't see nearly as far as what we have been for the last couple of days, but still 70 miles is quite a good distance away from the summit. And then taking a look at the vertical temperature profile, this comes from our mesonet, the series of weather stations that start at the summit and go all the way down the side of the mountain to the base, recording things like temperature and wind. As you can see, we have a pretty standard temperature profile. Most of the temperatures are decreasing as you get higher and higher up the mountain. There's a little bit of cold pooling going on at the base, but I mean, you're down there in the 60s, and then up here, we're still down in the 50s. And so this is pretty much the descending temperature profile that we've grown used to. And so again, it is just a very calm, clear, and stable day up here on the top of Mount Washington. Now, we have a lot to talk about today in regards to tornadoes, and so we're going to go ahead and dive right in. Of course, if you guys have any questions, we will have a Q&A at the chat, as I'm sure there will probably be lots of interesting things that you want to know. So let's go ahead and dive right into the presentation. Without missing a beat, today we are talking about tornadoes and how they form and evolve over time. Now, I want to preface this entire presentation by saying there is still very much that we don't know about tornadoes, and research is ongoing and has been for several decades, but these systems by nature are incredibly chaotic and incredibly difficult to measure. So today's presentation is going to focus on one of the things that we have come to determine is more accurate within the research of the last few years in regards to tornadoes and how they form and evolve. So let's go ahead and dive right into it. What is a tornado? Now, a tornado is a narrow, violently rotating column of air that extends from the base of a thunderstorm all the way back down to the ground. And that is the true most important part of that definition, is that the tornado has to be making contact with the ground in order to technically be considered a tornado. Otherwise, it is a funnel cloud, which we'll talk about here in just a little bit. Now, tornadoes often form from violent or severe thunderstorm types. Typically, we can see them with squall lines, but more often than not, we see them associated with supercell thunderstorms that you guys talked about with Tom in the last presentation. So we'll be focusing strictly on supercell tornadoes for today. Now, as you can imagine, tornadoes are essentially a formation of an incredible amount of energy from the thunderstorm itself focused into a very tight area at the surface, and that can cause incredible amounts of damage and destruction, which is one of the reasons why tornadoes are one of the most beautiful but also some of the most dangerous natural phenomena that we can witness. And so they are incredibly powerful, and they could be relatively small if you're looking at a lower rated tornado, sometimes a couple hundred feet across, all the way up to 2 miles wide or more. They can grow massive on the order of the EF5 scale, which we'll also talk about here in a little bit. Sometimes tornadoes are stationary. They'll make contact with the ground and barely move around at all before they lift back up. Some tornadoes can travel incredible distance, hundreds of miles, depending on what kind of atmosphere they're moving through as the system progresses. And they usually move at a pretty decent speed. Sometimes they move about 10 to 20 miles per hour, but some of the more fast tornadoes can move upwards of 60, sometimes even 70 miles an hour across the ground, kind of like your car on a highway, which is pretty fast, all things considered. And they can last for a couple minutes. They might touch down and swirl for like 3 or 4 minutes and then lift back up, or sometimes they can last for several hours. And one of the more impressive tornadoes we've seen in our history lasted for 3.5 hours and traveled 220 miles and caused an incredible amount of damage in its path. You might have heard of it before, the tri-state tornado. We won't have time to talk about it today, but I highly recommend you look that system up because it was really impressive. So that's what a tornado is, and I'm going to go ahead and jump into full screen so you guys can see this graphic better. Now, you may be aware that the United States is actually the tornado capital of the world. We actually have a considerably favorable atmospheric setup that allows us to see an impressive amount of tornadoes each year, which we'll talk about here in just a moment. The graphic you're looking at here actually represents a focus on the number of strong tornadoes per 2,500 square miles. As you can see in the legend here in the bottom right, as we're looking at different sections of the graph, you can see areas that have seen less than 1 severe, like EF3 or greater tornado, all the way up to greater than 15. And as you might be noticing immediately, there's a pretty heavy concentration here in the eastern plains, the Great Lakes, the Mid-Atlantic, and then down here in the southeast. And so this is what we know as Tornado Alley. Now, Tornado Alley, interestingly enough, has been expanding and moving over time with the effects of climate change. And just because it's focused here in this neck of the woods doesn't mean that all the other parts of the country are exempt from really strong tornadoes. You can see up here, even in New England, down in Massachusetts, and Rhode Island, and Connecticut, have seen some impressive tornadoes over the last 50 years. And so it doesn't have to be located in the Central Plains. Tornadoes can form anywhere that the conditions are favorable in order for them to do so. So what goes into creating Tornado Alley, and why is the United States the capital of tornadoes across the world? It has a lot to do with the continental setup, with the Rockies being right here and the Gulf Coast down here, creating this boundary right here that we know as the dry line. Now, the dry line is a separation of cold, dry air to the left side on the Rockies and warm, moist air on the right side. Now, what happens at night is the dry line actually recedes and moves west as warm air floods in and pushes in off of the coast of the Gulf of Mexico. Now, over the course of the night, this cold, dry air will pool and build, and then following sunrise and throughout the day, this cold air will redescend down the Rockies and actually force the dry line back forward, colliding and pressing against this warm, moist air. As you might imagine, that creates an incredibly unstable atmosphere in this region as cold, dry air is forcing this warm, moist air to rise rapidly. That allows for the easy formation of thunderstorms, in particular supercells, and along with that, tornado formation. So as long as we have this atmospheric setup and the dry line moving back and forth west to east, we can see supercells and thunderstorms quite frequently throughout the year. So let's focus in and talk about supercell tornadoes, and let's talk about tornado genesis and how they form. Now, last week you guys spoke with Tom about supercells and their structure, but just as a quick review, I want to point out 3 key areas of the supercell that come into play. Starting with the updraft here. Now, the updraft is the central column of air that is taking warm, moist air from the surface and blasting it violently up through the atmosphere. And as it gets bigger and bigger, it starts to rotate within the supercell. We also have the forward flank downdraft here on the front side of the storm that's responsible for dispersing a lot of the precipitation. So right here on the front end is usually where we see the heaviest amount of hail, and then heavy rain and lighter rain as you move further and further out into the anvil. But the key player here in all this is actually the rear flank downdraft behind the storm. This rear flank downdraft is pulling a lot of really cold, dense air and precipitation down on the back side of the storm, but it's actually rotating around from behind the supercell, and this pulling and stretching of rotation is what's absolutely critical for tornado formation. So at most, focus on the updraft, and we're going to focus on the rear flank downdraft and their roles in what we call tornado genesis. Now, this is an incredibly complicated process with multiple steps that we're going to talk about here, and everything starts off with the formation of what we call a mesocyclone. Now, as the updraft of the supercell continues to ingest warm, moist air and it continues to grow, it will widen substantially as it does so, and it can be on the order of a couple miles wide to 5 miles wide or more. Absolutely massive, all within the supercell itself. Now, as the updraft grows bigger, it becomes more and more influenced by the wind profile of the atmosphere, and oftentimes with supercells, that profile is rotating as you go up through the atmosphere. So it too will start to rotate. The updraft itself will start to spin within the storm itself. Now, that is accentuated by the rear flank downdraft coming down behind the supercell and adding to that rotation. So what you get in an effect is this massive rotating updraft. It looks like the entirety of the thunderstorm itself is rotating. So what does that look like? What does a really well-formed mesocyclone look like? And it looks a little bit like this. Look how massive that is. That is literally the entirety of the storm rotating through the atmosphere, and it's kind of awe-inspiring but also a little bit terrifying. Imagine being on the ground, seeing this move towards you. It's absolutely impressive. So this is step 1, the formation of this mesocyclone in the tornado formation process. Now, the next step here is the formation of the wall cloud. Whoop, I jumped to the wrong screen there. There we go. So the formation of the wall cloud. So as the rear flank downdraft continues to pull and stretch that rotation down, it will pull it and stretch it, and it becomes thinner and more focused. Imagine the analogy of the ice skater. When the ice skater kind of pulls herself in tight, she starts to rotate faster and faster. And the exact same thing is true in this case here. So what happens is the rear flank downdraft stretches that rotation down. That rotation will pick up moisture from the mid-levels of the storm, rapidly force it downward and force it to condense and form this wall cloud-like structure. It kind of looks like the wall cloud itself is actually extending from the base of the storm, which is very much the case. And so it's like a little mini mesocyclone rotating underneath the bigger one above it. So what does that one look like? So let me go ahead and step out of the presentation here real quick. I want to show you guys a brief video so you can see what this wall cloud looks like. So I'm going to go ahead and just play in this view here, but you can see this is the wall cloud extending down from the base of the mesocyclone, and watch as I hit play as it rotates through. And these two can be pretty large and impressive by comparison, but you can see the very slow rotation of this extension beneath the storm, progressing and extending just above a couple hundred feet above the surface of the Earth there. And so once you see the formation of a wall cloud, you're pretty extensively along in the formation of tornadoes. So let's go ahead and jump back to our presentation here. So first we had the formation of the mesocyclone. The rear flank downdraft pulls more rotation towards the surface and forms the wall cloud. The next phase then is the formation of the funnel cloud. And this is getting close to the very final stage of tornado genesis. This is the final extension of the rear flank downdraft and rotation to the surface. And the funnel cloud actually doesn't make contact with the ground. So these are not the tornadoes themselves, but they are absolutely essential for the final formation of the tornado. And so again, it's just hovering just above the ground there. Oftentimes looks like it is making contact with the surface, and people mistake these for tornadoes, but they have this kind of thin, ropey-like structure, and oftentimes have a very small conic-like structure to them as well. And as long as they're not making the ground, they are very much their own separate entity, and doesn't necessarily mean that the tornado is going to form. So what's happening with this is now we have an incredibly focused, tight rotation happening just above the surface of the Earth. And that very tight rotation is beginning to influence the air directly at the ground level. So this is the final phase of tornado formations. When you have this funnel cloud stretching down, influencing the air at the surface, we get to the final process of tornado genesis. Oh, sorry, we'll get there in just a second. I want to briefly recap all the structures that we've moved through thus far. So we have, again, the mesocyclone formation up here in the upper parts of the storm, the wall cloud forming as the rear flank downdraft brings that rotation closer to the surface, and then underneath this massive wall cloud, we have the condensation funnel, or what we call the funnel cloud underneath. So these are the first three phases, but even if you make it all the way to this point, it doesn't necessarily mean you're going to get a tornado. There is one final thing that needs to occur, and this is ground rotation. So what happens here, like I said a moment ago, is that the funnel cloud above is greatly impacting the surface of the Earth and causing rotation at the ground level. But there's one more obstacle that this rotation needs to overcome. At the surface, we have things like trees and tall buildings and other large objects that are creating friction and making things really difficult as far as rotation goes. So what needs to happen is the influence of the rotation aloft needs to overcome the force of friction at the surface. If that happens, what you get as a result is an incredibly intense rotation right at ground level, so much so that it creates like a vacuum effect and starts to pick up debris and lift it up into the atmosphere. So you can see in the picture here, you've got lots of dirt and debris right at the ground, and you get this invisible column of rotating air extending upwards into the sky. So it's very much like lightning. When we talked about how lightning forms from the ground up in some cases, so too does the same thing happen with tornadoes, that this ground rotation will extend from the surface up and up and up into the atmosphere. And when it makes connection with that funnel cloud, that's when we get tornado formation and what we call a touchdown. So what does that look like? What does this ground rotation look like? Let me jump back to full screen here so you guys can see. Look at this rotation of dust and debris at the surface extending really high up into the air, but beyond a point, you can't see it anymore. Not enough debris has lifted into that part of the atmosphere for you to be able to see where the rotation is occurring. But if this continues to extend upward and make connection with the funnel cloud, that's when we get the tornado. So let me step out of the presentation again. I have another video I want to show so you can see what that final process looks like in full. So just 1 second here, we're going to go ahead and get the video started, but a couple of things I want to point out real quick. This tornado is going to touch down and pick up multiple times over the brief period I'm about to show, but what you should be paying a lot of attention to is right here at the surface, looking for that ground rotation to stretch from the ground, make connection with the funnel cloud, resulting in the tornado. So let's go ahead and check this out.
I don't even think I'm going to use it actually. Just go ahead and put it back up, Colt, because we're going to have to move on this thing. We're going to have to, it's steady with me right now. It's steady with me right now. Just go ahead and put that back up, put it back in the car.
And there it is right there. So you could see that initial swirling of air picking up that dust and making connection with that funnel cloud. And now we have the full-blown tornado here. So really impressive. Again, a lot of people assume that tornadoes form from the cloud and go all the way down to the ground. But the opposite is true, is that you get the funnel cloud, which influences that ground rotation and then creates enough force to lift that debris up, make connection with the funnel cloud, thus resulting in the tornado. So very interesting stuff that we've only recently discovered with research in the last 5 to 10 years or so. All right, so how do we evaluate tornadoes and how do we rate them, similar to like how we rate hurricanes? So we use what's called the Enhanced Fujita Scale, or the EF rating, which is actually based on damage and the amount of damage done by the tornado in relation to its wind speed. So you can see the ratings from 0 to 5 on the left there. You can see their wind speeds, and then it goes from light damage at an EF 0. So you might have some shingles blown off your roof, you might have some small trees snapped over, some branches knocked down, all the way down to 200 plus mile-per-hour winds in an EF5 tornado. These are the storms that are absolutely devastating. These are the ones that can wipe an entire town completely out or can damage large portions of cities. These are the incredibly dangerous, scary, and deadly tornadoes. And then we have all the different damage values that we can see in between. I highly recommend at some point you go back in the presentation and check this out and to see if you've ever witnessed or experienced or heard somebody talk about these type of damages before, and see if you can relate it to particular tornado strengths. But this is the scale we use, and again, it's in relation to damage versus the wind speed that the storm was putting out. So how do we evaluate tornadoes and how do we study them? And the primary way that we do that is through the use of radar. And we actually make use of these two radar products here that we call reflectivity and radial velocity, which I'll talk about both of them here. So we'll start with reflectivity, and essentially what the radar is doing is sending a signal out towards the storm, and that signal is going to be intercepted by raindrops or debris or like large heavy objects and send a signal back to the radar to be detected. Now things that are less reflective, like little raindrops and maybe tiny sized hail, will have these kind of light greens and yellows, but very reflective objects like large hail or debris will show up in these reds and these pinks. Now the classic supercell structure kind of has a kidney bean shape to it. And then down at the bottom, if we're in the middle of a tornadic event, we're looking for this part here that we call the hook echo. And within that hook echo, again, it kind of looks like a hook here, we look for this structure here, which is highly reflective signals that are coming back to the radar. And this is pretty much representative of debris, what we call a debris ball signature when we're looking at reflectivity. So this is one very good indicator of tornadoes, or at least tornado formation, when being detected by radar. The other product we use is called radial velocity. So what we're looking at here is how air is either moving away from the radar, which is the reds that you're seeing here, or towards the radar, which is the greens that you're seeing here. Now the lighter and brighter colors are generally indicative of very fast moving air, and when we see either side right along the boundary there showing very incredible values for both going away or coming towards the radar, swirling around each other, that is what we call a couplet. And the presence of a couplet, also with the presence of a debris ball, is a very good sign that we're seeing a tornado on the ground. And so these are two very reliable products that we use for observation, forecast, and research of tornadoes. And when we see these things pop up, that's when we're going to start to put out warnings and start to advise the public. So I wanted to show this picture because at one point in time in a life before the observatory, I was a storm chaser. And this is a really good picture of one of the instruments and radars that we use to study tornadoes. And in particular, this is called the Doppler on wheels. So it has the massive radar here on the back mounted on this powerful truck. And this is incredibly beneficial because we can drive and position the radars where we want them to be in order to analyze tornadoes. Now, we do collect data from stationary radars as well, and there are stationary weather radars all across the country, but it's not total coverage. We don't have radars covering every single part of the surface so that we never miss a tornado, and we also can't move them and position them how we want. So these Doppler on wheels and these mobile radar systems are incredibly beneficial because they can drive right up to the storm itself and start to analyze it up close and personal. You can get multiple radars positioning around the storm and get different angles and different perspectives and really good data. So the invention of these mobile radar systems has been absolutely crucial for tornado research and tornado studies. You can see I'm very, very much excited to be standing next to one of these from a couple of years ago. So this is one of the major factors in which we use to study tornadoes and to try to better understand them. Now, a lot of people like to ask, when should I be concerned about a tornado? When is it absolutely crucial that I start to act and start to prepare? And that's pretty much the case with basically whenever there is the tornado threat in your area, you should at the very least have a plan and have a good idea of what you want to do. And there's a lot of confusion between tornado watches and tornado warnings, or severe weather watches and warnings in general. So I wanted to show you guys this graphic to try to clear the air. Now, a tornado watch means that the conditions are favorable for a tornado to form. There isn't anything that's being picked up yet, no tornado reported on the ground, but the conditions are favorable for things to come together and for a tornado to form. So that's usually the yellow box indicator. This is when you should start to be concerned and start to prepare and plan in the event that you upgrade to a warning, which are the red boxes. Now, a warning gets put out when a couple of things happen, either when a tornado is actually visible on the ground, like somebody reports it, calls it into the National Weather Service that somebody actually spotted a tornado on the ground, or by radar indicated storms. When we're seeing that high reflectivity, when we're seeing the rotational velocities of a storm, we put these polygons out for tornado warnings, and if you find yourself in that area, that's when you need to immediately start taking shelter and start acting to prepare yourself for the storm incoming. Now, you can get this watch and warning data from your local TV news, from radio stations. You can tune into AM band on your radio to find the weather channel that's constantly providing updates for weather in your neck of the woods. You could also set your phone to get emergency alerts from the National Weather Service and other organizations, and it will send you notifications and text messages for tornado watches and tornado warnings directly to your mobile device. So all of this is incredibly helpful to let you know what's going on in your area. And at the bare minimum, most towns and cities have tornado sirens that will go off whenever the region that you're in falls under a tornado warning. They're very loud and they're very ominous, and I think they're a little terrifying. But when you hear those sirens going off, if nothing else has happened, if you haven't tuned into the radio or tuned into your phone, this is the time that you need to immediately plan, act, and start taking shelter. So what does this look like? What are some things that you can do to protect yourself in the event of a tornadic event? So the very first thing is have a plan. Have some kind of idea well before you even find yourself in this situation of what you're going to do, where you're going to go, and what's the safest place for you to be during these really strong tornadoes. And not only have the plan, but also practice it too. It's really nice to put something down on paper, but if you never try it out, how are you supposed to know if it's going to work? So have a plan, make the plan, practice the plan, and then make sure you have an emergency kit too. So you've got supplies like a first aid kit, maybe some food and rations if you might be stuck there for a long period of time, but having that emergency kit is just the nice added benefit to help you stay safe once the system has moved off. Identify where you're going to go at home, but also what you're going to do maybe if you're at work or if you're at school. And along with that, have some kind of communication plan with your family. If you are only relying on landlines, that's okay, but what if the power gets knocked out or the lines go down? If you guys have cell phones, make sure you stay in constant communication with each other if you're all not at home, and just have some kind of plan and structure in place to communicate with each other during these really extreme events. So having a plan and having a communication system is key. And then let's say that you're right in the middle of the event. What can you do? So the best thing for you to do is to be inside of a solid structure, something with 4 walls, a roof, and support structures throughout. And you want to get to the lowest floor in the most interior room of that building, whether that's a bathroom or a closet on the first floor or down in the basement there, something that doesn't put you higher above the ground in these parts that are more susceptible to being damaged by the tornadoes. Find the interior lowest place that you can be. And also, protect yourself. Cover your head, whether that means with a blanket or a quilt, or if you happen to have helmets, that would be fantastic too. And then once you are there, stay there in place. Even after the storm has moved off, you need to wait a considerable amount of time for this system to move away for a number of reasons. There might be still debris flying around even though the tornado has progressed away from your house. There's always the threat of lightning with these events, and of course the structural stability of your house itself. So you need to wait in place until long after the event is over before it's safe for you to go out. So do not leave your house to go follow the storm. Don't be like running up to your front porch with the video camera to capture it. Stay where you are in this interior room and wait things out. Now let's say that you're not at home. What's the best thing that you can do? Well, first of all, you should never try to outrun a tornado in your car. The very best thing you can do if you're caught outside is to find a ditch and get as low or below ground as you possibly can. Things like overpasses are a terrible idea because they actually create like a suction force underneath that can blow debris and cars and rip people out from underneath there. So you want to just try to find the lowest part of the ground that you can possibly be in the event that you cannot find a structure that is stable for you to be inside. So that's a little bit about tornado safety. We'll end the talk here with one of the most historic storms that's ever been reported, and this is the El Reno, Oklahoma tornado of 2013. This is actually one of the tornadoes I did my master's research on because it was just an incredible storm. A massive EF5 tornado that spanned 2.6 miles wide, making it the widest tornado on record in the United States. It saw a maximum wind speed of 302 miles per hour. That's 71 miles per hour faster than the previous world record wind speed that we saw up here on the summit of Mount Washington. $40 million in damage, which doesn't seem like a whole lot, but the fact of the matter is this tornado progressed through a rural area, and caused that much damage without really impacting a major town or a city. So that in itself is thoroughly impressive. 151 people injured, 8 people killed, 4 of which were storm chasers. So this was an incredibly deadly and dangerous tornado, and it was there on the ground for a very long time, for 40 minutes, and it traveled just over 16 miles around the city of El Reno. So a really dangerous, impressive, and deadly storm, and I have some video footage so you can see what it looked like that I want to show you here. So we'll jump to the video. Here we are. A couple of things that I want to point out really quick. Use this as an opportunity to identify the different structures of the storm, so see if you can figure out where the mesocyclone is, where the wall cloud is, the funnel cloud, etc. And you're going to see at some point that the tornado is so large that it actually fills most of the entirety of your screen. So try to find the areas of a wedge-like structure. That is the edge of the tornado. So let's go ahead and dive into this video here and just take in the impressiveness that was this storm.
That is ugly, ugly tornado. Look at the size of that monster. Jesus. There goes. Look at that. Jesus. Man. Holy cow. Alright, this is gonna get really ugly really fast here. Look at that. God. This is ugly. I gotta stop and take some pictures.
The multiple vortex tornado was moving faster now, growing in size, and while tailgating a line of other vehicles, I calculated a direct hit, so I whipped the car around and headed back west. At this point, the tornado is at peak width, a 2.6 mile wide EF5, the widest tornado ever recorded.
So as you can see, just a tremendous, dangerous, and deadly event. That was one of the most profound and historic tornadoes that we've seen in our history. And storm chasers in particular, when I was doing storm chasing a few years ago, we all kind of have this sombering moment when we know that there's a potential for a tornado to hit a large populated area. Of course, we get excited and passionate about studying these systems, but there's that fear and that worry that so many people are going to get hurt, and it's a very realistic thing. So these are very dangerous systems, and hopefully the safety today kind of help figure out what you can do in these particular events. But that is the tornado presentation. That's as much as we know, at least as much as we can talk about in this time frame for today. So a couple of things I want to point out to you really quick. Of course, you guys can head to mountwashington.org/classroom to get more information, to check out our schedule in the coming days. So you can see tomorrow we're going to be doing our forecast discussion, so make sure you check that out. Also, there is the worksheet there and the activity for this week, which I'll talk about in just a moment. And of course, you can go back and look at some of the previous episodes in case you missed one, the lightning, the severe storms, all of these really good topics that we've covered over the past few weeks. And so you make sure you want to check that out. In regards to the worksheet, this is this week's worksheet, so you can go through and better understand storms. You get an idea of how they form within supercells, the different types of tornadoes, the different damage ratings with the Fujita scale. Lots of really good information here. And then this week's activity is a tornado simulator. So up there at the top, you can actually mess with how wide the funnel of the tornado is and the internal lack of pressure within the storm. We call it the pressure difference. Set it to go off and see what kind of damage and destruction it does. And so a really cool opportunity to check out different types of tornadoes and how strong and how much damage they can do. And so definitely check out this week's activity and have fun with that. At this point, we'll turn it over to questions if we have any. So Jay, what do we got?
We have a couple questions.
Sure.
Christina wants to know if debris in a tornado is thrown out to the sides or if it goes all the way up. And if it does go all the way up, what happens then?
Yeah, so that's a very good question. So the debris within these tornadic systems can actually go in both or all of those directions that you mentioned. So they can be blown outwards at hundreds of miles an hour, which themselves actually can do considerable amount of damage. A lot of people like to believe or assume that that tornado debris actually is responsible for most of the damage just before the tornado hits, followed by the strong winds. Now, if they are lifted vertically and thrown away from the storm, they can actually travel a considerable distance. And I don't know what the actual record is for the largest amount or the furthest a debris has moved away from a tornadic cell, but I have heard instances of tornadoes moving over ponds and sucking up like frogs and fish and throwing them like dozens of miles away, so that the people who are away from the tornado, suddenly it's raining frogs and fish, which is really kind of disturbing and gross, but it is very much a thing that can happen. People have been picked up in bathtubs and thrown incredible distances, so yeah, it's a combination of both outwards and upwards and outwards. So yeah, very good.
So you're saying that when tornadoes go over the water, they can actually suck up the fish?
Yep, and the frogs too.
Cool. That was our next question.
Oh, okay. Yeah, it's really gross and really sad, but yes, it is a thing that can happen.
Another question we have is, how do you know when a tornado is coming at night and you can't see it?
So that is a very good question, and night tornadoes are some of the most deadly for that very reason. This is when radar comes into play incredibly importantly. So being able to identify high points of reflectivity in the sense that can we see a debris ball on the radar signature, and also looking at velocity to see if there's rapid swirling at a very concentrated point. Using radar can very much help clear the air. It doesn't solve the problem completely, but it is an incredibly useful tool for nighttime forecasting for tornadoes, and hopefully can save a lot of lives.
Our last question is a doozy.
Oh boy.
Can tornadoes split into two over water and or land?
Yeah, so that is a very good question. So I think there's multiple questions going on there. So we'll start with the last one. Can a tornado go from land to water and vice versa? And yes, absolutely. It's more likely for a tornado that's formed on the ground to progress out over the water before it dissipates. But it's a lot more difficult for a tornado to go from a water environment where there's very low friction onto land. You got a lot more trees and buildings and things in the way that can actually destabilize the structure of the tornado if it's not strong enough. But there have been many times in recorded history where water spouts, those water tornadoes, have progressed onto land and grown into full-blown tornadoes. And tornadoes themselves can split into two. You might have seen in the El Reno video, there was actually the main tornado itself and multiple vortices swirling around it. We call those suction vortexes or suction vortices, little mini tornadoes that rotate around. And so the tornado itself can break down into these little suction vortices and reform. Supercells themselves can split into two and progress along. So this splitting process is a common thing that does occur with tornadoes and tornadic supercells. So yeah, great questions today. If there are more in chat, I promise I'll try to get to them and answer them in the comments today. Thank you guys so much for tuning in. Again, this was a really exciting talk for me. Hopefully you enjoyed it. And then tune in tomorrow at 11:15. We'll be doing a forecast discussion for the lovely, pleasant weather we've been experiencing for the last week and a half. And so it's going to be a really good time. Make sure you guys check out the classroom page, mountwashington.org/classroom. Check out the worksheet, check out the activity, and then hopefully we'll see you guys tomorrow at 11:15. Thank you so much. Enjoy the rest of your Memorial Day.